Can? Are you done calculating this angle? What's the angle?
5.1.
5.1. Do you get this? Here you can do the algebra.
But then like how do you know that the 70/35 one is also a ion?
It's written there what?
Isotopes.
No, it's an ion. Look at the charge.
The 70 one.
They also say what?
Oh, is it okay? Huh? Oh, can I flip the next page? Okay then. Can? Yeah, complete out this question. Try part 2 as well. When you're done with part 2, show me. I want to see your deflection. Okay, you done with part 2? Okay. Hey, don't get 5.1, Hui Yen. I never go and do the algebra. But
Well, please go and calculate there. Your algebra so weak.
I think I can. 1/70 times 5 divided by 1/2.
Okay, so make sure you show your deflection the moment it enters the field. So this is positively charged ion. It should deflect to the negative plate. Can? Hui Yen?
Yeah.
Faye, okay, Faye? Yes, Okay, I move back to the lecture already. Gerald, you okay, Gerald?
Yeah.
You write 5.1 degrees, right?
Huh?
You write 5.1 degrees.
Yeah, you can write that if you want. Okay, I move back to the...
Sure, I'm eating.
Okay, can you all see my screen? Yeah.
If it's a nucleus on its own, right, then it's always to
The proton number.
then is it always deflected to the negative plate?
Yes, because it will be positively charged. Nucleus is always positively charged. Ion can be positively charged or negatively charged. Can?
Yeah.
Can? Okay, let's move on. Let's move on. Okay, so far you have seen this type of notation. We call this a standard notation. You have to know. Okay, the top one is your mass number. The A is your mass number. The Z is your proton number. Okay, must know how to interpret this. I want you to know that this is different from your periodic table. Periodic table is reverse. On top is your proton number. Below is your mass number. Okay. Okay, so do not get confused. Okay, now let's try this. Okay, you need to make sure that you are able to identify the number of protons and neutrons and electrons inside the particle. Ken, are you done with this? All of them? Okay. Do you get these numbers?
Wait, isn't the the 40 supposed to be 3?
Why 3?
What's 37 minus 34?
37 is for 1 chlorine atom. There are 2 chlorine atoms here.
Isn't nitrogen supposed to be 8 neutrons?
Sorry. Yeah, this one is 8. Okay, do you get all of them? Okay, Huyen, okay?
Yeah.
Can I move on now? Okay, now let's move on to this quantum shells, subshells, and orbitals thing. Okay, so what you learned in O level last time, it looks like this. It's something called a Bohr model. By A level, we do something called the quantum mechanical model. So that's why we bring in these new terms: quantum shells, principal quantum shells, subshells, and orbitals. Do you all know what are these type of terms?
I watched your video. Cause this one you got filmed.
Faye, do you know what are these type of things? What is principal quantum shell? What is subshell? What is orbital? Faye, do you know? Okay, what is a principal quantum shell to you?
The number like 1, 2, 3.
Okay, how about orbitals?
The shape.
The shape. Okay. Huyen, how about you? What is orbitals to you?
The place that they can move within.
Okay, the place that they can move within. Okay, never mind. Let's go through it. Okay, so what you have learned last time in O level, okay, all these type of shells, okay, we call them the principal quantum shells. So this is n equals to 1. The one inside is the n equals to 1. Okay, next one is n equals to 2 quantum shells. Ken, what you learn in your O level, these are principal quantum shells. Ken, I think this is what Faye is referring to as well, yeah? Okay, so this is principal quantum shell. It's nothing new to you. You have learned this in secondary school already. Okay, now take note, the maximum number of electrons that can be contained within each shell is given by this formula, 2n squared. So for n equals to 1, it can contain 2. For n equals to 2, it can contain 8. For n equals to 3, it can contain up to how many if n equals to 3?
18.
18. Okay, so therefore, what you learn in secondary school about octet rule, it is not true. Okay, what you learn about octet rule in your secondary school is not true. It's only applicable for period 2. Okay, next thing. Remember in chem bonding, we said that period 3 and beyond, if it expands octet, it's okay. Okay, the reason for that is because of this, because they can contain up to 18 electrons. Clear? Okay, so those who just came for camp bonding recently. Okay, next thing, what are subshells? Okay, so if you have n equals to 1, it means that you will have one subshell. If you have n equals to 2, means you have two subshells. Okay? Which is over here. Okay? So the n equals to 1 means that there is one S subshell. N equals to 2 means that there are two types of subshell, the S and P subshell. Okay? An analogy for this is, you can think of it like a HDB. Okay, I'm going to skip this a while. You can think of a HDB. Okay? So n equals to 1, n equals to 2 is like your levels in your HDB. Okay? So what I'm telling you is this, and n equals to 1 at the first level, okay, there is only one type of apartment, okay, which is a one-room apartment. For n equals to 2, there are two types of apartment, which is the S and P apartment, which is the one-room apartment and the three-room apartment. Okay? Okay, so this is an analogy for you to think about it. Atomic principal quantum shell is the levels in the HDB. Your subshell is the type of apartments at that level. Okay? Okay, and the orbitals is, let me go back. Okay, and the orbitals is the rooms inside the apartment. Okay, so the 1s subshell, the one room apartment only has one room. Okay, the 2s subshell, which is the one room apartment as well, only has one room. But the three-room apartment will have three rooms. Okay? Okay, so therefore your p orbitals will have, your p subshell will have three orbitals. And each of the orbital can contain 2 electrons. Okay, so therefore if you look at this, this is why if it's n equals to 1, it can contain 2 electrons. If it's n equals to 2, it can contain up to 8 electrons. Can see that? Can Okay, let's move on. Okay, now the p orbitals, they are degenerate. Okay, what does degenerate mean? Okay, over here you will see this word. They are degenerate orbitals. Okay, degenerate means that they have the same energy. Meaning these are the three-room apartment. Okay, all the rooms are equal. There is no preference for any of the rooms. Okay, I know in Singapore you got master bedroom, you got other room, blah blah blah. Okay, but what we are assuming over here that all the 3 rooms are equal. Okay, they are degenerate, which means that there is no preference for any one orbital. Okay, so even though when you learn atomic structure, you will know that we always fill in from left to right, correct? Okay, but it is by convention. Okay, if you choose to, you can always fill up like that if you want to. Nothing wrong, but just to make life difficult for yourself, lah. But by right, there's nothing wrong. Follow what am I saying, guys? Because there is no difference between the p orbitals. P, X, P, Y, P, Z, they are all the same. Because they are degenerate. Okay, so far? Each orbital can contain 2 electrons, I already told you. Now, how do the orbitals look like? Okay, so orbitals, you know there is the shape of the orbitals. Okay, later on I'll explain a bit more about this. Okay, we know that the 1s orbital looks like this, it's like a sphere. Okay, the 2s is a bigger sphere, and the 2p is like a dumbbell shape. Okay, now, why do they look like this? Okay, why do they look like this? You must first understand probability density. Okay, so for some of you who haven't watched my videos, okay, I just want to find out what do you know about orbitals. Okay, I think Huyen, you have already watched this part, so I won't ask you. Faye, what about you? What do you understand by orbitals? You mentioned that there are something about the shape, right? Why do they look like this?
I don't know.
Okay, Gerald, any idea? Gerald, you should know this one. You came for the workshop the other time. Hey, Gerald, you here or not?
I don't know, the electrons. When
the electrons what?
Observe the electrons, then they all appear around that direction, that area.
Okay. Pretty much there already. Okay, so first of all, you need to understand probability density. Okay, in order for you to understand probability density, you must first understand how electrons move. Okay, electrons in your secondary school, what you learn about electrons? Huyen, what do you learn about electrons in secondary school?
Move around in
In secondary school, your teachers tell you they move around the nucleus like that, right? Like the stars around orbit, correct? Not stars, like the planets around the orbit around the sun. Sorry, stars don't move. Okay, a lot of you learn that electrons orbit around your nucleus like how the planets orbit around the sun. Okay, but that's a misconception. Electrons do not orbit. Clear? Please get that this concept out of your head. No, they do not. They do not orbit. Understand not, Huyen? Okay. So to understand how electrons move, I'm going to show you a video. Can you see? Can you see my screen?
Yeah.
Can Okay, I'm going to fast forward. I'm going to show you exactly how electrons move. Okay, so if you can see my screen, this is how electrons move. All these things are electrons. The way they move is this. They will disappear and appear somewhere else. Can Fei? Okay, they will disappear and appear somewhere else. Okay, this is what we mean by probability density. Okay, in other words, you cannot see your electrons move like a car like that. You cannot see it move from point A to point B. It doesn't move like a car. It will teleport. Okay? It will disappear from here and appear another place. That's why we call it a probability density. Okay? Which means within that space, okay, there's a 95% chance to find the electron. Follow what am I saying, Faye? Okay, which means this, if I want to find out where is the 1s orbital, where is the 1s electron, maybe it appears here. Watch the screen. Maybe it appears here. Next moment, what will happen? The electron will disappear, appear somewhere else. Follow what am I saying? Now, if I measure it 1 million times to see where the electron appears 1 million times, what you will see is this. And then each time I take a picture, and then I combine all the pictures together. This is what you will see. One instant is here. Next instant disappear, appear here. Next instant appear here, disappear, appear here, disappear, appear here, disappear, appear here. So if you combine 1 million snapshots of it together, you realize that the 1s electron is found inside this region of space. Follow what am I saying? So that is why it looks like a sphere. Okay? This sphere here tells you the region of space in which the electron has a 95% chance to be found. Clear? And if it's the 2p orbital, if I want to measure how the electron looks like, maybe it looks like here. At one instant it's here. Next instant disappear, appear, disappear, appear, disappear, appear, disappear, appear, disappear, appear. Then you combine all of them together, you realize that the probability density looks like that. Can you understand this, Faye? Can? So this is what we mean by orbitals, okay? It is the probability density. So that's why it looks like this over here. Hey, where's my mouse? Okay, if you look at the diagrams here, okay, can you see all the individual dots over there? Can you see or not? All the dots. Okay, all the dots there show you where an electron was found. Okay, so if you combine all of these dots together, we come up with the shape of the orbitals. Okay, so as your n increases, your electron can be found in a wider region of space, so that's why your orbital size will increase. Can your 2s is larger than your 1s? Can? Okay, so I'm going to show you another video. Okay, so if we combine them all together, okay, we combine them all together. Last time you thought atom looks like this, but let's look at how it actually looks like if you combine all the orbitals together. Okay, this is how the 1s orbital looks like. Inside here, got how many electrons? Got 2 electrons in here. Where are the 2 electrons?
Anywhere.
Don't know where. Somewhere in there. Understand not? Somewhere inside here got 2 electrons. Inside this region of space, there's 2 electrons. I do not know where the 2 electrons are exactly. I just know that it's somewhere in there. Clear? Next is the 2s orbital. Inside here we have another 2 electrons. Clear? Inside this whole thing got another 2 electrons. Somewhere in there. I don't know where, but somewhere in there. Next, this is the 2p orbital. Okay, we call this the 2px because it's oriented along the x-axis, the red color line. This is the x-axis, can see? Next, the 2py means it's oriented along the y-axis, which is the green line. Inside here got another 2 electrons. Somewhere inside here, okay? Not 1, it doesn't work like that. It's not 1 electron on this load, 1 electron on this load. Doesn't work like that. It's 2 electrons somewhere inside this entire region of space. Clear? Okay. Lastly is the 2pz oriented along the blue color axis. Inside here got another, can contain up to another 2 electrons somewhere inside here. Clear? So if you put them all together, your atom is actually 3-dimensional. Can you see? This is how the atom actually looks like. Okay, so if I compare that with my Bohr model, okay, last time you think electrons look like this, okay, but in actual fact, it looks like this. Okay, so let's compare neon. Okay, 2.8. 2.8. In your secondary school, you learned that this is 2.8. Where is this 2.8? Inside this 1s got 2 electrons. Okay, inside the 1s got 2 electrons. Inside the 2s got another 2 electrons somewhere in there. Follow what am I saying? Inside the 2p got another 2 electrons. I'm going to put inside here. Inside the 2px got 2 electrons. Inside 2py another 2 electrons. Inside 2pz another 2 electrons. Follow? So the electrons are not okay, it's not over here surrounding your nucleus and orbiting around your nucleus. They actually look like this 3-dimensional model. Are you all very clear on this? Clear? Okay, so Huiyan, what is the orbiter?
The place that they move is like 2px, 2py.
So if the exam asks you how to define an orbital, you will say that. Based on what I just said, what is an orbiter?
A region of space in which there is 95% probability of locating the
Hey, don't read off the notes, come on. Layman terms, quick.
place that the electrons move in.
Yes, okay, so the orbiter is a region of space in which there's 95% chance to find an electron. Can? Faye, okay? Can you understand orbiter already? Faye, okay, Faye? Can, Okay, so this is what an orbiter is. It's just a region of space in which you can find an electron. Now, next question. Do orbiters exist even if there's no electrons? What do you think? Do orbiters exist even if there's no electrons? Yes, yes, the orbiters can just be empty. Actually, all the orbiters are always there, just that they are not filled.
The orbit is like the room.
It's just a region of space, ma.
The rooms, right?
Yeah. It's just a region of space. Follow what am I saying? It's just like on a school day, Huiyan has 95% chance to be found in the canteen. Follow what am I saying? It's just a region of space, okay? But now CB Huiyan is at home, but once school starts, she will still have a 95% chance to be found in there. The region of space is always there. It's just whether it's empty or not. Follow what am I saying? Okay. Now let's move on to 3. N equals to 3. So n equals to 3 means got 3 subshells. So got 3s, 3p, and 3d subshell. And they can contain up to 18 electrons. Why? Because the 3d orbitals, there are 5 of them. Okay, so total they can contain another 10 electrons. Now you must know and learn the labeling for these. Okay, dxy, dxz, dyz, dx squared minus y squared, and dz squared. Now, what do these orbitals mean? Okay, you need to know dx squared minus y squared I'll go through these two first. Dx squared minus y squared and dz squared. This means that they lie on the axis. Okay, this is the name given to the orbital. Don't ask me why the scientists name them this way. They just decide to name them this way. Okay, dx squared minus y squared means they lie on the x and y axis. Clear? Dz squared means they lie on the z axis. Okay, like a donut with the in the middle. Okay, so far? How about dxy, dxz, and dyz? What do these names mean? Gerald, do you know?
Lie between those orbitals.
Yes, lie between those
Axes.
axes. So the dyz means it lies between the y and z axis. The dxz means it lies between the x and z axis. The dxy means lies between the x and y axis. Clear? Later I'll show you a video to show you. But first, let me teach you how to draw. Okay, if you are ever asked to draw, let me look for a blank space. If I ever asked to draw orbitals, I will show you how to draw all the orbitals. Common question in the exam, especially internal exam. I'll show you how to draw S orbitals first. Let's fix this axis x, y, and z. S orbital looks like this. Can you must label 1s or 2s. Can please learn, please draw. I'm teaching you how to draw. Can okay. So the S orbital must have the axis. If you draw a circle, only the school will mark you wrong. P orbitals look like this. Okay, let's do 2px. 2px means it's on the x-axis. 2py means it's on the y-axis. 2pz means it's on the z-axis. Can you know how to draw? I'm teaching you how to draw. Please draw together with me. And so for the s and p orbitals, we will not flip the axis. The axis we will fix it so that we can show the different orientation of the p orbitals. Clear?
Yeah, the first one can also be 3s, right?
Yeah, of course. Well, but usually we don't go until there lah. The p can be 3p also ma. 4p also can 5p also can. Can? Okay, next I'm going to teach you how to do the d orbitals. D orbitals is a bit harder. Okay, so which one you all want to draw first? Up to you all. You all want to draw the one on the axis or between the axis? Choose one. Between Nah, let's do it on the axis on the axis is easier. Okay, let's do 3d x squared minus y squared. Okay, so x squared minus y squared means it's on the x and y axis, correct? I'm going to switch my axis around a bit. I'm going to call this x and y. This one is on the plane. So it's on the x and y axis. Very ugly. Wait, let me redraw. Okay, it's on the x and y axis. So after you just have one thing coming out, which is the z. Okay. Okay. For 3D orbitals, I'll switch the axis around so that it's easier for me to draw. Okay. You need to know the axis is arbitrary. Look, meaning this let's say one is x, y, and z. You can always turn it around. Follow what am I saying? You can always turn it around. So therefore, the x, y, and z axis are arbitrary. Don't worry about it. Next, let's do the 3d z square. So 3D z square means what? It's on the
Z.
z axis. So let's call this the z. The rest doesn't matter. On the z axis, they must have a donut inside. Can? Done?
The X and the Y can switch place on.
Yeah. That's what I just said. They are arbitrary. Do you know the meaning of the word arbitrary? Means it is, I don't know how to explain to you. Arbitrary means it is not fixed. It is a relative thing. It's assigned arbitrary. Okay, I'll show you the next one. Between the axes. So let's do 3D XY, for example. Okay, so since it's between 3D XY, this one I'll call it this X and Y axis. Clear? So therefore, the loops are between the axes. You can see it now, it's between the X and Y axis. So the one coming out will be Z.
If the line pass through the oval shape.
Huh?
Must the line pass through the oval shape?
What do you mean?
The Z.
Nah, the Z is coming out, so I don't really care. That's why the Z I draw later. First you draw the dxy orbitals, that means between the X and Y axis, then the Z is just coming out. This one don't care. Can? Next, let's do the 3D XZ. So if it's XZ, what will be these two axes?
X and Z.
So let's say this is Z, this is X. Once again, between the axes. Okay, then coming out it will be your Y. You must learn how to draw this. You must learn how to label as well. You must know how to describe the orbitals as well. S orbitals are described as what shape?
Spherical.
And spherical and not complete.
Non-directional.
Non-directional. What does non-directional mean?
No direction.
What which means what?
Any direction.
That means there's no up. Okay? There's no up, but a ball is round. There's no up.
There's no
Up.
No.
There's no particular direction. Okay? A sphere is completely spherical. There's no like X or Y direction. It's not. There's no such thing. Okay?
You mean in this like 2px thing is like traveling forward or backward one kind of thing.
Huh? What? Is what?
You say electrons is like blink around one, so it's like
They are found inside this region of space.
yeah, but then they are directional, meaning they will move.
The orbital itself is directional, meaning it lies on the x-axis.
Oh.
But for the S orbital, you cannot say that it lies anywhere.
Okay.
Last one, 3D YZ. 3D YZ. So Faye, what will be your axis over here?
Y and Z.
Yeah, can? Doesn't matter which one. Then after that, just do in between again.
So in exam just need to draw like that and ready.
Yes. Can? So this is how you draw for the 3D orbitals. Cause it's not easy to draw, so you should flip it around. It will be a lot easier.
Then in the exam, they tell us to draw multiple, as in 3D XY, 3D XZ. Then you can just draw like that.
Yeah, of course.
Like side by side at least.
Yeah, and they all look the same, just that the axis is different. Okay, show you all the video for this. Can you see my screen?
Yeah.
Okay. Okay, this is the one S orbital. Inside here got 2 electrons. This is the 2s. Inside here got another 2 somewhere inside there, don't know where. Next will be the 2px. The 2px I think is the red color one. Yeah, the red color axis. Okay, so it's directional along the axis. Inside here got 2 electrons, can see? Got 2 electrons in there, don't know where, but somewhere in there. This is the 2py along the green color axis. Directional along the green color axis. Inside here got 2 electrons, don't know where are they. This is the 2pz directional along the z axis. Inside here got another 2 electrons, can? Now let's look at the 3s. Okay, I don't want to say already, I'm tired already. Inside here got another 2. Okay, 3px. Inside here got another 2. 3py. Inside here got another 2. 3pz. Inside here got another 2. Okay, then the 4s. Okay, because you know, fill in the 4s first and the 3d. So inside here got another 2. Yeah, this is how the 3D looks like. Okay, this is 3D z square. So watch, it is oriented along your z axis. Okay, 3D x square minus y square. So this one is where?
The axis.
On the x and y axis. So you will see, it will lie on the green color and the red color one. You see. Look at it going. It will lie on the x and can see on the green and red one. Can see or not? How about this?
This one.
It's between the axes. So you will, later you will see that it will be between the green and red one. Okay, take a look. Can you see? It's between the green and red one. Can you see or not? Exact is between the red one and the blue one. Can? Because the blue one is the axis. So inside here, okay, this YZ between the green and blue one. Inside here got another 2. Hey guys, you all know the d orbitals also contain another 2. But the region of space is like this butterfly thing. Follow what am I saying? Can? Okay, so inside here another 2, inside here another 2, inside here another 2. Can? Can? This is what it means. Cannot. So if you put all them together, this is how your atom looks like. Very complicated one. Can? You will never be asked to draw this. Don't worry. Can visualize this? Can? Okay, good. So you must be very clear on what orbitals are. Okay, now let's look at how do we fill in the electrons. But before that, okay, I told you all before, 4s is lower in energy than 3d. Okay, when empty, okay, when the orbitals are empty, 4s is below 3d. Okay, but you need to know this. The moment there is at least 1 electron in the 3d orbital, these two will switch. Okay, meaning this, the moment there is at least 1 electron in the 3d orbital, these two will switch. Okay, so this has implications on your ionization energy later on. Okay, why does it switch? This one is not in your notes. It's also not in your level. Cause at your level you just need to know 4s is before 3d. Can? But sometimes students ask me why, so I show them this. Can you see that the 4s is less than 3d? The 4s is below 3d at calcium and potassium only. Can you see that? The moment, look. The moment there is at least 1 electron in the d orbital, okay, the moment there's at least 1 electron in the d orbital, can you see that 3d now becomes lower than the 4s throughout? Can you see that? Can? Okay, don't understand this one, never mind, just know The moment there's at least one electron in the 3D orbital, these two will switch, can? Then the 4s will become higher in energy. Okay, now how do we fill the electrons? We follow 3 rules. The first rule is something called the Argon principle. Okay, meaning we fill up from the lower levels first. Okay, so if you look at this, after 3p, we fill in 4s, then 3d, can? Okay, so you can think of it like a double-decker bus, okay, or multiple levels like a HDB. Okay, to fill up the energy, we fill up the lower deck first, then we fill up the higher deck, can? Because you can think of it this way, electrons are like people like that, very lazy, right? They don't want to go upstairs, can? So they will just fill up everything below. Then once below all fill up, then bopian, they have to climb up, can? Because climbing up takes energy, same thing for electrons, can? Next thing, next rule you need to know is something called Pauli's principle. It means that they cannot have opposite spins to each other. Sorry, what did I say? No, they must have opposite spins to each other. They cannot have the same spin, sorry. Okay, they cannot have the same spin. They must have opposite spins to each other. Okay? So using the bus analogy as well, it means this. If you are going to sit with somebody, you want to, if I'm a guy, I want to sit with a girl. Okay? Make sense? Okay, last rule, Hund's rule. It means this. If there are degenerate orbitals, which means there are multiple rooms, okay, and all the rooms are the same, they will prefer to occupy the room singly first. Okay, once again, you can think of a bus. Okay, in general, you think of it, in general, you think of it in reality, okay, when you go to a bus, this is what you see as well. People will sit alone first before they pair up, assuming they're not with friends, okay? They will sit alone first and occupy all the seats singly first, and then when you go up, all the single seats are occupied, then you bopian, you will go and pair with somebody. Make sense? Can? Okay, just like now social distancing, okay? So they will sit alone first. Can? Can? So let's try this. Oh, it should be quite simple for your faster fill in and fill in the electronic configuration also. Then I can quickly move on. Okay, so write the electronic configuration as well. For electronic configuration, please do not put a comma or dot or anything. This is how you do the electronic configuration.
So, but then, like example for the 4BE, right? I thought you say like it will occupy the orbital singly first, so it's supposed to be
If they are degenerate orbitals. Degenerate means what?
same energy.
Yeah, so are the 1s and 2s, are they same energy? Hello, are they same energy? No, right? So you have completely filled out the 1s first and then the 2s. Are you all done? Can I assume that you all get it correct? This one is very simple. I move on now. Okay, so now let's go to transition elements. Okay, for transition elements, you have to fill in the 4s first before the 3D. Okay, so this is how we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, fill in the 4s first, then the 3D. Okay, and if they are degenerate, fill them up singly. Okay, so this is 1s2, 2s2, 2p6, 3s2, 3p6. But when you're writing the configuration, we do not write the 4 first. We must go with the 3D, 3, then 4s2. Can? In terms of writing. Can you give me the electronic configuration for Argon? Three S2, 3p.
3p6.
Yeah, okay. So therefore, I need you to know that this one, okay, this part here is Argon. Can see or not? Until here. Can see? So another way we can write configuration is Argon 3d6 4s2, 3d3 4s2, sorry.
Oh, that means you are supposed to fill up 3s 2 electrons first before you go on to 3p, right?
Of course, yeah. Why?
Oh no, because previously I fill up everything first, singly first.
No, cannot. Those in lower energy levels must be completely filled up before going out. This is the first rule, the Akbar rule. And for iron, what is yours? Sugar, argon, 3d6, 4s2, right? You get it?
Yeah.
Okay, so you should look at this. Okay, of course, everything else in front filled up, I lazy fill up. When should you give this configuration and or this? When?
When the question
Do you
asks,
know? What if they want the left one? What would they say?
Full electronic
Yes.
configuration.
Okay. If they ask for full electronic configuration, you must give the left one.
oh,
Okay. If they ask for full electronic configuration, you must give the left one. Otherwise, if they just ask for electronic configuration, the right one is fine. And the right one is called the condensed one. Okay, but must have the AR. You don't just put the 3D 34S2. Must have the AR over there. Okay. Okay. Now, two anomalies you have to know. Okay. Chromium. If you follow the rules for chromium, you will get this. Agree or not? Okay, but this is an anomaly. One of the 4s will come down. Okay. So it will be blah 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 blah. 3d5 4s1 is an anomaly. Clear? Why don't need to know? Just know that these two transition methods are anomalies. Can?
so the question when asked explain like
No,
why.
not for these two. Not for these two. For the main group elements, yes, but not for these two. These two you just need to know only. Okay? For copper as well, you will expect it to be 3d9 4s2. You will expect it to be this, but once again, one of the 4s will come down. So it will be 3d9, sorry, 3d10 4s1. Can your schools will give you a reason in the notes, but then that one fake one can, so don't bother.
No, what's the real reason?
Much more complex than that. Your schools will say something about symmetrical charge distribution, inter-electronic repulsion, but that one bullshit. What your school put?
Write a very long paragraph.
What your school put? Terry, what your school put?
Inter-electronic repulsion.
For both Oh. Gerald, what your school put?
Isn't my school your old school?
Yeah, so what your school put? Every year they change one, so what they put now? Say what your school put?
The closed energy level of 3D and 4s allow rearrangement of electrons to achieve a configuration of lower total energy for 3d5 4s1 and 3d10 4s1 by having one electron in 4s orbital the inter-electronic repulsion is minimized. And then still got another one is half filled or fully filled 3D subshells are energetically more stable due to symmetrical charge distribution.
That's symmetrical charge distribution. Yeah, Faye, what about you? What your school put?
It's more stable,
Why?
more symmetrical 3D electron clouds.
See, every school also gives different one, right? Okay, Terry school is inter-electronic repulsion. So that's why this one don't need bother. They will not ask you one. It's not one of the learning outcomes. And the reason is fake one. Okay? That's why I don't even have any reason here. Because the reason, I can put but whatever reason I tell you will be a fake reason, so I don't bother. Okay? The reason is fake one. You just need to know that it is more energetically stable with this type of configuration. Yeah, that one is true. That's all. It is more energetic. This configuration is just more energetically favorable.
As in they want to be high energy or low energy?
No. They just want to be like that for various reasons. Okay, so don't need to bother about reason. Just know that these two anomalies will exist. Can only for these two. Please don't give me for anything else. Only for these two. Okay, next I need to teach you how to write electronic configuration for ions. Okay, so what you need to do first is to write the atom and then remove or add in electrons. Can? So do the atom one first. So this is 1s2, 2s2, 2p4, I think. Okay, if it's O2 minus means add in 2 electrons, so it's 1s2, 2s2, 2p6. Okay, if you are asked to remove electrons, you remove in the reverse order in which you add. Can? So you remove this one. Okay, remove the last one that you added in.
You add into the 4s first and you also remove from the 4s first.
No. Yeah. For transition methods, yes. We are. I actually this to something else, right? What is in your notes? Carbon.
Yeah.
Carbon. And carbon what? 2 minus
Minus.
Minus.
Yeah, just minus.
Can? Okay, if it's transition matter, I think it's 3D5 4s2. Okay, we fill out the 4s first, but we also remove from the 4s first. Because remember, it will go higher in energy after there's at least one electron in the D.
We don't know, right? Because I find it very hard. So I just like remember if remove and add into the 4s first.
Yes, that's correct.
But then
But if you understand why, then I mean it's not difficult to understand why. At first it's below when it's empty, so you fill in first. But later on, when 3D got electron, it will switch So the 4s now become higher, so you remove from the 4s.
Oh, okay. But then if it's transition matter, then it determines if it's not transition matter, then you don't remove and add into the 4s first.
If it's not transition matter, you won't even go to 4s.
Okay.
Only pass the transition methods, then you go into the 4s. Same thing for copper. Okay, remove from 4s first, then the 3D. Can? Now, okay now. Now I want to teach you a shortcut to determine electronic configuration. Meaning I want you to be able to look at your periodic table and immediately come up with the configuration. Can? You cannot take so long to come up with the configuration. I hope by now you are not doing the configuration by counting the electrons. Huiyan, are you doing that? Wei, are you doing that? Do you know how to read the periodic table and come up with the configuration? Yes, okay. So please don't go and count. Huiyan, do you know how to look at the periodic table and do the configuration?
Yeah, I think so.
Okay, so don't go and count. What I mean is this. Okay, you all must be able to come up with the configuration in 3 seconds. So for example, if I ask you phosphorus, Fei, what's the configuration?
1s2, 2s2, 2p6, 3s2, 3d3.
Yes, good. Can? Okay. Huiyan, if I ask you calcium, what is it?
1s2, 2s2, 2p6.
3 seconds over.
3d2. 3d6, 3d2.
3s2.
3s2.
Hey, how come your configuration all over the place one?
3d.
Okay. This is how we do the configuration. Watch. The first one is 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. So the periodic table is very smart. After 3p, they fill in the 4s. Can see or not? 4s1, 4s2. Then 3d1, 3d2, 3d3. This one anomaly. 3d5, 3d6, 3d7, 3d8, anomaly, 3d10, 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. Follow what am I saying? Everything over here is the P block. You just need to see which period it is. Here is period 1. Here is period 2. Here is period 3. Here is period 4. Can? So which period it is will depend what is the number in front. Can? Then here is the S block. Can see or not? Then here is the P block. Can see or not? Can? So if you want to very quickly come up with a configuration, I'll show you. So for example, like the one I asked, wait, let me erase all this first. Okay, so for example, like the one that I asked Huiyan, like calcium. Calcium, you look at this, this is 4. In which block?
S.
S what? 4s2. Can see or not?
Yeah.
Immediately, you can see? It should take 1 second. Then you fill out everything in front. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Can? Can? So you must be able to do this immediately. Can? Are you able to do that? Can give you some examples. If I want boron, oxygen, and neon, come, give me the configuration in 3 seconds or less. Okay, boron. Huiyan, tell me, boron.
1s2, 2s2, 2p, 1s1, 2s2.
1s1.
Wait, I need to see the thing. I cannot. Wait. 1s2, 2s2, 2p6.
Hello, where's boron? Boron here.
p1, 2p1.
Hey, how are you? Korean, silicon.
Huh?
Silicon.
1s2, 2s2, 2p6, 3s2, 3p2.
Yes. Can? The rest of you okay, right, Gerald? Terry, okay?
Yeah. But I got one question.
Yeah.
Like for the anomaly, right? Does that
Yeah.
mean like the whole row is like anomaly, or just chromium alone?
You mean here?
Yeah,
Actually, yeah.
the whole thing.
Yeah. Until here, here I don't know already. The next one, I know the next period also same, but the below that I don't know. Can? Cause got the F coming also. Can, Terry? Can?
Also, before the F come in, the whole.
You don't bother. You only know until here. You don't bother. You know until here can already. Can? You can do until here. We very happy already. Can?
Okay.
Can? All of you can do until here. We very happy already. This is what you are tested on. Okay, we take a 3-minute short break. You all go toilet first. Okay, take a 3-minute short break before I move on to IE. Okay, if you are done, can you look at your tutorial question 9, 10, 11, 12, 13, 14? Yeah, 9 to 14. Can you try? Your tutorial 9 to 14. Okay, for 9, the answer is D. Is that okay?
Oh wait, I want to ask.
Hmm.
C2 plus also is it?
Which one?
You.
Which one?
Copper.
Copper is what?
2 plus also.
Where?
Like if it's transition metal.
Uh-huh.
Like confirm because it's
I don't
transition
understand your question. Can you
No,
ask a
it
full
can be like
question?
Cu plus also.
Yeah.
That it will affect the electronic configuration.
Yes.
So how do you know what charge is it?
They have to tell you.
But they didn't tell.
Which one didn't tell you?
The first one.
9? 9?
Yeah.
No charge what?
But I think
9A
yeah, never mind. Yeah.
What,
But
what are you talking about?
What do they mean by similar outer electron configuration?
Means the electronic configuration is the same, the valence electron configuration is the same.
As in, if someone has 4s2, the other one also has 4s2.
Yeah.
Or 4s2 and 3d2 also can.
No. You mean one is 4s2, one is 3d2?
Yeah, just as long as there's
No, that's not same. Same means the same.
That means like example 1s2 and 2s2, is it the same?
No. Nine is D, okay or not? Any question for that? No, that?
Also correct.
Which one?
Number C.
C. Tell me the configuration for copper 2 plus.
3d7 until 3d7.
Huh?
Right.
How come until 3d7?
Because they lost 2 electrons
From where?
from 3d9.
Then your 4s eh?
Mr. Lau,
Yeah.
no paired 3D electrons means the spins like not opposite, right? Is it?
Again.
No paired 3D electrons means like the spins not opposite, right?
No paired. No paired means all unpaired. Yeah. Means all the spins are the same direction. Yes, Huyen. What is the configuration for copper 2 plus?
3D 9.
Yeah. Then magnesium?
2P5.
2p5? Hey, walao, hey, how you come with your configuration one?
Cause at first is 3s2, right?
Yeah.
Then after they minus 2, then it will become 2p5 lor.
Hey, tell me the full configuration for magnesium.
Until 3s2.
Tell me the full electronic configuration for magnesium.
2s2, 2p6, 3s2.
This is magnesium. If magnesium 2 plus,
Sorry. Wait, is it 2p6?
of course. Anyhow, you don't anyhow give me configuration, please. This one is your foundation. You cannot do this, you cannot do IE already. Okay, so D, 9D, okay not D? Huyen is still at D, it's still at 9. Hello, Huyen, are you still at 9?
I did 10 and 11, just I skip 9.
Ten is D as well, 10.
But anyways, the Fe2 plus is actually 3d6, right?
Yes.
Okay.
And 10 is D, okay not? Faye, okay? Gerald, okay, Gerald? Okay, 10 is D. 11 is B, 12 is D, 13 is B. I leave this here. Let me know if you got anything you want me to go through.
Actually, in our papers, the answer is already highlighted in blue.
Of course, I give you the soft copy.
Yeah.
No, then you can print black and white. You can print black and white.
With color.
You can print color? What's wrong with you?
I don't know how to change.
Wow, too rich already.
Huh?
Just print color ink like that. Hey, any questions for 11, 12, 13?
I'm trying to like read that. I feel like 9 is more hard.
9, you understand why is it D?
Cu has 3 and then Mg 2 plus.
Write the electronic configuration. Write the configuration. Tell me the configuration.
Of who?
Copper.
1s2, 2s2, 2p6, 3s2, 3p6, 3d9. Sorry. 3d10.
我要打人了。
10. 3d10.
Oi, not done.
4s2. 4s2.
No. Stop it. Stop anyhow giving me configuration. Well, you anyhow you want to say what you just say.
Very hard. 4s1.
You sure or not? You don't anyhow hunt down one number
Because come down one, yeah.
Then magnesium 2 plus. 3 seconds over already.
1s2, 2s2, 2p6.
And?
Just 2p6.
Yes, so it fills until the n equals to?
Oh, okay, wait, I understand already. No, because I didn't think of
2, n equals to 2. This one fill n equals to 4. Because you anyhow do your configuration, that's why I cannot do.
I cannot like read straight away from the periodic table.
Cannot. You must be able to do so. That one, no compromise. You must be able to do so.
But for aluminium, I thought they also got 3 unpaired electron for question 12. Because there are 3.
Tell me the configuration for aluminium.
1s2, 2s2, 2p6, 3d2, 3s2. 3d. I say I want to.
Hey, I want to smack people already. What?
I wanted to say 3s2. I say wrong. 3p2, 3p3.
You look at your periodic table and tell me again.
No, because I saw the group number. Okay,
No, you look at your. I don't care what you see. You look at your periodic table and tell me again. What?
2p1. I understand really.
Anyhow, Huiyan.
No, I didn't. But I saw the group number.
No.
Like 3.
No. No. Look at your periodic table. Don't anyhow give me my configuration. Hey, are you done until 14? Everything okay? 13 is B, 14 is C, okay not? Faye, okay?
For 14, the first one is wrong. Is it cause it should be 3D subshell?
Yes, okay, exactly. 3D orbital can only contain 2 electrons.
Okay, thank you.
Huiyan, okay, Huiyan?
I'm at question 13. Yeah, I'm done.
Okay, let's move back. Okay, let's start to explain what is ionization to you, ionization energy. Tomorrow we will go into the more chim stuff. Today is just to settle the foundation. Make sure that all your foundation is okay. Okay, meaning electronic configuration. You must be able to come up with electronic configuration quickly and accurately. And that's the foundation to do IE. If you cannot do that, you cannot do IE. Am I clear? Okay. Tomorrow we will do all the more chim stuff. Today is still quite basic stuff. Yeah. Now let's talk about ionization energy. What is IE? Ionization energy is simply the amount of energy required to remove the electrons. If it's the first IE, means to remove the first mole of electrons. Okay, the equation is represented as such. Okay, take note, they will ask you to write this equation. You must have the state symbols. Can? I repeat, you must have the gaseous state symbol. This is the definition for ionization energy. Can? Second IE means remove the second electron. Can? That's why you're removing it from N plus because the first electron already gone. Clear? Okay, so this is how it looks like. Look at this animation here. First IE means, where is it? First IE means remove the first one gone. Can? Similarly, from your energy level, it is the opposite. Can? Meaning the last to be added will be removed. So this one will be removed. Second IE means remove the second one, become M2 plus, clear or not? Okay, remove the second one. Can this is second IE? Understand what am I saying? Can try this. Tell me your third IE of calcium.
Ca2 plus gas to Ca3 plus gas plus 3E minus.
Plus,
3E minus.
do you all agree? You all agree? No, No, What's wrong?
Electron thing.
How many electron?
Just one.
Sorry,
One.
I say wrong. I say wrong.
No, sorry, no cure one. Exam wrong means wrong. Yeah, exam wrong means wrong. Third IE means remove the third electron by only removing one. Clear? Okay, next. What is this? What is this? Which IE is this?
A summation of 1, 2, 3.
Okay, so this one is first IE plus second IE plus third IE. Okay, so far? Can Okay, now let's look at the factors that affect ionization energy. Okay, there are in general only two factors, which is your nuclear charge and your shooting effect. Now, what is nuclear charge? Nuclear charge refers to the number of protons. The larger the number of protons, the higher the nuclear charge. You can think of, I'm going to give you an analogy. Think of it as a campfire. This is you. The heat that you feel from the fire is the attraction to the nucleus. Clear? I repeat, the heat that you feel from the fire is the attraction to the nucleus. Clear? The higher the amount of heat, the stronger the attraction. Make sense? Can? So therefore, when you have a higher nuclear charge, it means that your fire is larger. If your fire is larger, do you feel more heat? Yes. Now, the next thing that affects ionization energy is something called shooting effect. Okay, you heard of this in your school, shooting effect. Now, what is shooting effect? Shooting effect is the number of inner electron shells. So according to this analogy, it means how many people are there sitting between you and the fire. The more people there are between you and the fire, they will shield you from the fire. Make sense? They'll prevent the heat from the fire reaching you. Agree or not? The higher the shooting effect, that means the more people there are between you and the fire, the lesser heat you feel. Make sense? So therefore, you feel less attraction to the nucleus. Okay, so far? So you need to understand that these two factors work in opposite directions to each other.
Wait, so the shooting effect is not talking about the person next to you, but the person in front of you, right?
Yes, the person between you and the fire. If it's next to you, they do not shield you at all. You think of real life example. If your friend sitting beside you, do they help you at all to make the fire less hot? No, right? Make sense, Huyen? The shooting effect is just the people between you and the fire. And you need to understand that these two factors work in opposite directions. The higher the nuclear charge, the greater the heat. The higher the shooting effect, the lesser the heat. So that's why the net heat that you feel from the fire, we call that the effective nuclear charge, which means at the end of the day, you look at these two factors, what is the amount of heat you feel from the fire? Okay, and it's given as this equation here. Okay, the nuclear charge minus the shooting effect. Now, you need to understand that this is not a real mathematical equation. This is not math. So Huyen, you'll be very happy. This one is not math. It is just a qualitative explanation, okay, to explain that these two works in opposite directions. Can? This is not a real mathematical equation.
So when it's meant to use like effective nuclear charge?
To see the net overall effect, lor.
So overall is you look at the effective nuclear charge.
The effective nuclear charge will determine whether your first IE decreases or decreases, increases or decreases. But usually we don't talk about it, we talk about the first two. Then because with the first two we can make a deduction on the effective nuclear charge already.
What if they have the same shielding effect?
Meaning the shielding effect don't increase, is it, or what?
Yeah, it doesn't increase.
Which is the next example. Now across the period, can you see that across the period the IE in general increases? If you look at your periodic, if you look at your data booklet as well, if you look at the first IE in general across the period, do you see that it increases? Can you see that? Now, what happens across the period is this. Across the period, okay, what happens to your proton number?
Increases.
It increases. You got more protons, which means your nuclear charge increase. Agree or not?
Yeah.
Across the period, your fire gets bigger. But across the period, you also got more electrons. Agree?
Yeah.
Where are your electrons?
The outermost.
They are in the outermost shell. In other words, if you look at this analogy here, I'll show you the animation again. Across the period, your nuclear charge increases, so your fire gets bigger. But where are your electrons added? They are added beside you. Agree? They're added on the outermost shell. They're added beside you. Make sense? So therefore, do they shield you from the fire?
No.
No, which is what you're asking. The shielding effect will remain constant. So what do you think is the net effect?
On the nuclear charge.
So the fire gets bigger, but you got more electrons, but they're sitting beside you. They don't help to shield you. So what's the net effect from the fire? You feel more heat or less heat or same heat?
Same heat.
More heat lah.
Sorry, more heat. As in, I'm talking about the person sitting, the effect of...
I'm talking about you. What's the net effect when the fire gets bigger? You got a fire bigger, but you got more electrons, but they're sitting beside you. So what's the net effect? Do you feel more heat or less heat?
More heat.
More heat, right? Makes sense, Ken? So this is the explanation across the period. That is why your first IE across the period increases, Ken? Because in general, your proton number increases, but your shielding effect remains constant. So therefore, your net attraction increases. Hence, you require more energy to remove the first electron. Can I understand this? Can I? Okay, this has implications on radius as well. So this same explanation, besides affecting the first IE, so across the period, your first IE will increase. It also causes your atomic radius to decrease across the period. Okay, why? Because across the period, nuclear charge increases, shielding effect remains constant. There's greater attraction on the outermost electrons, which means it will pull the outermost electrons closer together, resulting in a smaller radius. Can you understand this? Okay, it also affects something called your, I'm going to skip this. It also affects something called your electronegativity. Okay, what is electronegativity? If you learn from chem bonding, electronegativity is how much you love your electrons. Across the period, your electronegativity increases. It gets more and more electron loving. Why? Because nuclear charge increases, shielding effect remains constant. There's a net increase in...
Wait, can you say again?
Again?
Like this part again.
Okay, across the period, what happens? Nuclear charge increases, shielding effect remains constant. Correct? So what happens to your net attraction?
More attraction.
More attraction, which means across the period in general, it likes electrons more. That's why electronegativity will increase across the period. Make sense?
Yeah.
Because electronegativity means how much you like electrons.
How much that the nucleus like electrons?
How much the atom likes electrons.
Oh, okay.
Can, but because the nucleus now higher nuclear charge, so they will pull all the electrons closer to itself. Okay, so that's why if you see across the period, the electronegativity increases. This has implications on chem bonding, yeah? Okay, and the radius will decrease. Can you understand this? Can, Faye? So remember when we were doing chem bonding, we talked about lattice energy, we talked about the ionic radius. Across the period, it will decrease. Can you understand why now? Can I? Now, across the period, there are two anomalies you see as well. Okay? in general, it increases, but there are two locations that it drops. Can you see? From beryllium to boron, if you look at the figure, it drops from 900 to 799. From nitrogen to oxygen, it drops from 1400 to 1310. Okay? Okay, why? Let's look at these two anomalies. Okay, the first one, from beryllium to boron, there's a drop. Why? Because your outermost electron in boron is in your p orbital. Okay, think about it this way. P orbital is higher in energy. The 2p orbital is higher in energy than 2s. When it's higher in energy, what does it mean? Do you know what does this energy level mean? If it's higher, what does it mean? More or less stable?
Less.
Less stable, agree? If it's higher in energy, it's less stable. If it's lower in energy, it's more stable. Do you all know this? Yes, you must know this. So therefore, if it's in the 2p orbital, which is higher in energy, okay, it also means that that electron is less stable, so less tightly held. In a way, you can imagine that? It's less tightly held, so therefore it doesn't take as much energy to remove it. That's why there's a drop. Make sense? Make sense? Korean, Ken?
Yeah.
Okay, so the reason we use here is that the 2p orbital is higher in energy than the 2s orbital. Hence, some schools will say that the 2p orbital is further away than the 2s orbital. Some schools will use that. I personally don't like that, but the schools will accept it. Okay? So whenever you see this anomaly, these two anomalies, one is due to p orbitals higher in energy, you will use this reason. The other anomaly is due to something called inter-electronic repulsion. So it occurs from nitrogen to oxygen. Okay, nitrogen, if you write out the configuration, is 1s2, 2s2, 2p3, which means the 2p orbitals got 3 electrons, which are singly occupied. Oxygen is 1s2, 2s2, 2p4. There is a pairing of electrons here. There's a pairing of electrons here. So when electrons are paired, what does it mean? There will be repulsion, inter-electronic repulsion. Follow what am I saying? When there's inter-electronic repulsion, it doesn't take as much energy to remove them. Give you an analogy. Okay, for example, okay, if I put someone you don't like to sit with you, there will be repulsion between you. So if later on I say, oh, Terry, I need you to shift seats. Okay, it doesn't take as much energy for me to make you shift your sitting arrangement. Follow what am I saying? Because you are quite happy to get rid of that person. That's what it means. Can I understand what am I saying? Can? Huyen? Can? So therefore, the two anomalies is only these two. Higher in energy, p orbitals higher in energy than s orbitals, and inter-electronic repulsion. Can? But I need you to know it doesn't only occur from beryllium to boron and nitrogen to oxygen. Please do not remember it this way. Okay? Do not memorize the elements. Tomorrow I'll teach you, because when it goes to second IE, third IE, fourth IE, it will be different. Understand what am I saying? I'll teach you a more general method to identify when to use it. Okay? But for now, I just need you to know we have learned 3 reasons so far. Okay? The first reason is the general trend across the period. The second reason is the second and third reason is the 2 anomalies. Okay? I'll teach you when to apply. All you need to know is know how to apply. That's all. Understand what am I saying? Okay? Let me see this. Okay, so your homework for today is question 15. I just need you to do 15. Hey, wait, can you look at your... I sent you something called a sample questions, right? Yeah. Can you look at the sample question, the first question? Is it the same as 15? Should be the same, I think. Is it the same? Yes, yeah. Can you just do the first question in this sample question? Because it will lead on for tomorrow. Okay? So you can see in part B, there's something called second IE. So I need to show you all this tomorrow. Okay? Tomorrow, I will teach you how to apply this reason. That means these reasons, okay, you need to know these 3 reasons are fixed. Can? In your entire syllabus for atomic structure, there are how many reasons? Do you know?
6.
There are 6 reasons, okay, given to you over here in your this cheat sheet. So tomorrow I'll teach you how to use this cheat sheet. Have you printed out this cheat sheet? Okay, there's this cheat sheet. There are 6 reasons. Today we covered which one? Today we covered reason 1. And
1, 5, and 6.
1, 5, and 6. Okay, today we covered 1, 5, and 6. Okay, I need you to know that the way we explain it is always the same reason. The only thing is, do you know when to apply it? That's all. Okay, total got 6 reasons. Tomorrow I'll teach you when to put in the 6 reasons. Okay, so today you have learned 3. Follow what am I saying? Okay, so all we need to do is recognize the scenario in which that reason should happen, and then copy and paste, insert the reason in. Can?
Oh, wait, but I got one question.
Yes.
You know the one that you say that the effective cancer. Wait, what page is that? The effective nuclear charge thing, right? Nuclear charge can also be like in opposite to the other reason one. There's 3 things, right? One is nuclear charge. One is
No, there's only 2 things.
effect.
Nuclear charge and shooting effect. There's only 2 reasons.
The number of principal quantum shell.
That one ignore. That one ignore for now. Can? For now, you just need to know these 2 reasons: nuclear charge and shooting effect. Can? Can?
Then when to use the atomic radius, the variation in atomic radius?
That one tomorrow. Can? So for today, I just teach you 3. Can? And I want you to know that you shouldn't memorize these elements. Can? Today, I just want you to know you shouldn't memorize these elements. Wait, let me go back to the... Are you seeing my screen or the... Oh, you're seeing my screen. Okay. So as I was saying, you all have this cheat sheet, right? Today we have done reason 1, 5, and 6. Okay, I need you to recognize that it doesn't just apply for beryllium to boron and nitrogen to oxygen. Understand what am I saying? Beryllium to boron, nitrogen to oxygen only applies for first IE. If it's second IE, third IE, it will be different. Okay, tomorrow I'll teach you how to recognize. But all you need to know is, once is this reason, you just copy and paste this reason, put it inside. It's the same reason. Can? Can? Any questions for today? Today should be relatively simple. Today is just building the foundation for tomorrow, which means your electronic configuration. Understand? Koya, I'm looking at you.
I know.
Okay, any questions for today so far for 1, 5, and 6 for the 3 reasons? Faye, any questions? No, Gerald, any questions? No, tomorrow will be a bit more complex, because we'll be doing it first, second, third IE already. Okay?
But what? Wait. But the actual meaning of shooting effect is the repulsion of the inner shell electrons.
The actual meaning of shooting effect is when your electrons the electrons is the campfire thing.
I thought no, because we already see somebody say repulsion of the inner shell electron.
Is the somebody me?
I don't know. I forget already. I really forget already.
Does it sound like me?
Maybe not. Okay,
This is repulsion. This one is repulsion. This one is electronic. This one is shooting effect. Just think of the campfire. Can? Shooting effect means they sit between you and a fire. You got go campfire before? You guys should have, right?
Of course lah.
Yeah. So if you got people sitting between you and the fire, they shoot you from the fire. Agree? Yeah. Can just remember like that. Can? Any other questions? No. Okay. Then I will end here today. I'll see you tomorrow, same timing. Can?